Introduction. Amit and Sanjay are planning to purchase some articles from the market. For this, Sanjay is ready and waiting for Amit. Amit is combing his hair. After combing, when he puts the comb on the table and again picks the comb, then he gets surprised. He observes that some pieces of a paper are stuck to the comb. He shakes the comb well, but only few falls down, while others are still stuck to it. He asks Sanjay that why paper pieces are attracted towards the comb. Sanjay tells him that it was due to the attraction of charges. When you comb the hair, then comb gains charge due to rubbing. When this comb comes in contact with the paper, then opposite charge gets developed on the paper, and due to this, they both attract each other. Students, electric charges are present everywhere around us. Today we will study about the electric charges and fields. Objectives. At the end of this lesson, you'll be able to define electric charge, define conductors and insulators, know about charging by induction, understand basic properties of electric charge, define Coulomb's law, calculate forces between multiple charges, describe electric field, draw electric field lines, know about electric flux and electric dipole, analyze dipole in uniform external field, calculate continuous charge distribution, define Gauss's law and its applications. Electric charge. There are two kinds of charges: positive charge and negative charge. Like charges repel each other and unlike charges attract each other. If two glass rods rubbed with silk cloth are brought close to each other, they repel each other. If two plastic rods rubbed with silk cloth are brought close to each other, they repel each other. If one glass rod and one plastic rod is rubbed with silk cloth are brought close to each other, they attract each other. Electric charge is a scalar quantity. SI unit of charge is Coulomb. Every neutral object contains an equal number of electrons and protons. When the number of electrons and protons are not equal, the object possesses a net positive or negative charge. Conductors and insulators. Materials are classified in terms of their ability to allow electric charge to move or be conducted through them. Conductors are materials that readily conduct electric charge. Metals are good conductors, for example, copper, silver, aluminium, and gold. In a metallic conductor, the number of free electrons that can move throughout the material is large. The exact number of electrons detached from each atom depends on the nature of the material. Insulators are materials that do not readily allow electric charge to move. Examples of good insulators are rubber, wood, glass, and mica. In an insulator, there are no free electrons. All the electrons are bound to their parent atoms and conduction of charge is not possible. Charging by induction. The process of giving one object a net electric charge without touching the object to a second charged object is called charging by induction. When a conductor is connected to the earth by means of a conducting wire, it is said to be grounded or earthed. Let's take an example to understand this phenomenon. Bring a negatively charged rod near an isolated uncharged sphere. As a result, the part of the sphere nearest the rod becomes positively charged and the part farthest away becomes negatively charged. Connect grounding wire to the sphere. Some of the electrons will now leave the sphere and move to the earth. Remove the ground connection. The conducting sphere is left with an excess of induced positive charge. Remove the rubber rod. The conducting sphere is now left with a net positive charge. Basic properties of electric charge. Additivity. The total charge of a system is the algebraic sum of all individual charges distributed over different parts of the system. For example, the total charge of a system containing 4 charges, 2 coulomb, minus 5 coulomb, minus 6 coulomb and 4 coulomb is equal to minus 5 coulomb. Conservation of charge. The total charge of an isolated system remains constant during any process. Charge can be transferred from one body to another, but it can neither be created nor destroyed. For example, grounding of the charge. Quantization. Any charged body has a total charge, that is, an integral multiple of a certain smallest amount of a charge E. The smallest amount of free charge E that has been discovered is the charge on an electron or a proton having magnitude 1.60 into 10 raised to the power minus 19 coulomb. Any charge Q on an object can always be expressed as Q is equal to NE, where N is an integer. Coulomb's law. The magnitude of the electric force exerted by one point charge on another point charge is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. The force is directed along the line joining the two charges. The magnitude F of the force between 2 point charges and separated by a distance r can be expressed mathematically as F is equal to K into mod Q1 into mod Q2 divided by r square. Here, K is a constant of proportionality. For vacuum and in SI system, Coulomb's law becomes F is equal to 1 upon 4 pi epsilon naught multiplied by mod Q1 into mod Q2 divided by r square. Forces between multiple charges. Superposition principle. For an assembly of charges, the total force on a particular charge is the vector sum of the individual Coulomb forces exerted on it by all other charges, the force between any two charges being unaffected by the presence of other charges. For a system of n charges, Q1, Q2, Q3 and so on till Qn, the total force F1 on charge Q1 due to all other charges Q2, Q3, Q4 and so on till Qn is F1 is equal to F12 plus F13 plus F14 and so on till F1n. This equation can be written as example. Let's take an example on Coulomb's law. Find the force on the center charge in given figure. Let's see the solution. Let F1 be the magnitude of the force with which charge Q2 is attracted towards Q1. We know that F1 is equal to 1 upon 4 pi epsilon naught multiplied by Q1 Q2 upon r square. Put the values in this equation. We get F1 is equal to 45 into 10 raised to the power minus 3 Newton, which is equal to 0.045 Newton. F2 is the magnitude of the force with which charge Q2 is attracted towards Q3. Put the values in the above equation. We get F2 is equal to 16.875 into 10 raised to the power minus 3 Newton, which is equal to 0.0169 Newton. Net force F experienced by Q2 is directed towards Q1 and is given by F is equal to F1 minus F2, which equals 0.045 minus 0.0169 Newton, which is equal to 0.0281 Newton. Electric field. There is a region of space around a charge or a system of charges within which other charged particles experience electrostatic forces. This region is known as an electric field. The electric field E at a point is defined as the electric force F experienced by a small positive test charge Q not placed at that point divided by the charge itself E is equal to F upon Q naught. The electric field E is a vector having the same direction as the force F on a positive test charge. The SI unit of electric field is Newton per Coulomb. The electric field at a point is given by E is equal to 1 upon 4 pi epsilon naught multiplied by Q upon R square into R cap. The superposition principle holds when calculating the electric field due to a group of point charges. E is equal to E1 plus E2 plus E3 and so on till En. This equation can be written as E is equal to summation from I equals 1 to n of 1 upon 4 pi epsilon naught multiplied by Qi upon Rpi square into Rpi cap. Electric field lines. Electric field lines are a kind of map that gives the direction and indicates the strength of the electric field at various places. The field lines always begin on a positive charge and end on a negative charge or at infinity in the case of a single charge. The number of field lines leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. No two field lines can cross each other. The relative closeness of the field lines indicates the relative strength of the electric field in various regions. Electric flux. Electric flux phi E is a measure of the number of electric field lines cutting through a hypothetical surface in an electric field. For a planar surface of area S immersed in a uniform electric field E, the electric flux is defined as phi E is equal to Es cos theta. When E is perpendicular to the surface, theta is equal to 0 degree and phi E is equal to Es, a maximum value. In this situation, a maximum number of field lines pass through the surface. When E is parallel to the surface, theta is equal to 90 degree and phi E is equal to 0. In this case, no field lines pass through the surface. For an arbitrary closed surface immersed in a general electric field, the electric flux is defined as an integral over the surface of E cos theta. The SI unit of electric flux is Newton meter square per Coulomb. Electric dipole. A pair of two-point charges, minus Q and plus Q, having the same magnitude but opposite signs, separated by a distance 2a, is called an electric dipole. The line joining the two charges, minus Q and plus Q, is called the dipole axis. The electric dipole moment P of an electric dipole is a vector pointing from the charge minus Q towards the charge plus Q and having magnitude equal to the charge Q times the distance 2a between the charges. P is equal to 2aq P cap. Dipole in an uniform external field. Let's consider a dipole placed in a uniform electric field E, with the dipole moment P making an angle theta with E. Force on charge plus Q is QE and on charge minus Q is minus QE. Since the forces are equal and anti-parallel, the net force on the dipole is 0. However, the two forces QE and minus QE form a couple. Magnitude of the torque is equal to magnitude of each force into arm of the couple. This equation can be written as tau is equal to cross product of P and E. Continuous charge distribution. The electric force on a point charge Q due to a charge distribution can be conveniently calculated by assuming the charge distribution to be a continuous one. Calculation procedure. Divide the charge distribution into infinitesimal elements. Find the force on charge Q due to one such element dq, assuming it to be a point charge. The resultant force on charge Q is obtained by the integration of the field contributions due to all other charge elements of the charge distribution. Linear charge density, lambda. This term is used when the continuous charge distribution is along a line and is defined as the total charge per unit length of the line. Its SI unit is Coulomb per meter. Surface charge density, sigma. This term is used when the continuous charge distribution is over a surface and is defined as the total charge per unit area of the surface. Its SI unit is Coulomb per meter square. Volume charge density, rho. This term is used when the continuous charge distribution is over a three-dimensional region and is defined as the total charge per unit volume of the region. Its SI unit is Coulomb per meter cube. Gauss's law. Gauss's theorem. The electric flux phi E through a Gaussian surface is equal to the net charge Q enclosed by the surface divided by epsilon naught, the permittivity of free space. Gauss's theorem is used to compute the charge inside a closed surface if E is known for all points on the surface. Application of Gauss's law. Field due to an infinitely long straight uniformly charged wire. As a Gaussian surface, we choose a circular cylinder of radius r and length L with its axis along the wire. If lambda is the linear charge density of the wire, the charge within the Gaussian surface is L lambda. We know that phi E is equal to integration of a closed surface of E dot ds, which equals to product of E and 2 pi rl, where 2 pi rl is the area of the curved surface of the cylinder. According to Gauss's theorem, we get electric field at any point at a radial distance r from the wire is equal to lambda divided by 2 pi r epsilon naught. Field due to a uniformly charged infinite plane sheet. As a Gaussian surface, we consider a circular cylinder of cross-sectional area A and height 2r with its axis perpendicular to the sheet. If sigma is the surface charge density of the sheet, the charge enclosed by the Gaussian surface is L sigma. We know that phi E is equal to integration over closed surface of E dot ds, which is equal to product of 2A and E. According to Gauss's theorem, we get electric field at any point at a radial distance r from the wire is equal to sigma divided by 2 epsilon naught. Field due to a uniformly charged thin spherical shell. To find the electric field at a point distant r from the center of the sphere of radius r, we choose a spherical Gaussian surface of radius r concentric with a charged sphere. If a rho is volume density of charge in the solid sphere, the total charge in the sphere is given by Q is equal to 4 upon 3 product of pi r cube and rho. Case 1. For points outside the solid sphere, r is greater than r. The electric field at any point distant r from the center of the solid sphere is equal to 1 upon 4 pi epsilon naught multiplied by q upon r square. Case 2. For points inside the solid sphere, r is smaller than r. The electric field at any point distant from the center of the solid sphere is equal to 1 upon 4 pi epsilon naught multiplied by rq upon r cube. Did you know? During rubbing, a body which has lower work function loses electrons and becomes positively charged. A body having higher work function becomes negatively charged by gaining electrons. Positron is a particle whose mass is the same as that of an electron. Positron has a positive charge of the same magnitude as that of the negative charge on an electron. Recently, the existence of particles of charge 1 upon 3e and 2 upon 3e has been postulated. These particles are called quarks. Summary. Let us summarize what we have learned. Like charges repel each other and unlike charges attract each other. The process of giving one object a net electric charge without touching the object to a second charge object is called charging by induction. Any charged body has a total charge, that is, an integral multiple of a certain smallest amount of charge E. The magnitude of the electric force exerted by one point charge on another point charge is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. The force is directed along the line joining the two charges. For an assembly of charges, the two force on a particular charge is the vector sum of the individual Coulomb forces exerted on it by all other charges, the force between any two charges being unaffected by the presence of other charges. The region of space around a charge or a system of charges within which other charged particles experience electrostatic forces is known as an electric field. Electric flux is a measure of the number of electric field lines cutting through a hypothetical surface in an electric field. The electric flux through a Gaussian surface is equal to the net charge enclosed by the surface divided by the permittivity of free space.